Hello everyone, and welcome to the companion video for the direct and limit comparison tests for infinite series. In the lecture, we introduced and defined the direct and limit comparison tests, and we looked at a few examples. In this video, we're going to look at some additional examples in order to really gain a better understanding of how these theorems can be used. For starters, I'd like to revisit the limit comparison test, and I'd like to take a look at a number of different examples. So let's write it this way. Let's go limit comparison test examples. So what I'm inspired by in this little mini conversation is that we saw in class that if I were to take a look at something like this series from, say, 3 to infinity of something like, let's say, n plus 2 over n minus 1 times n plus 1, what we see is that the numerator, the largest term, is an n, and the largest power term in the denominator is the product of the n and the n, so that's an n squared. So what we did in class is we want to consider the limit comparison test with, say, b sub n, which is the highest power term in the top, n, over the highest power term in the bottom, n squared, which simplifies into 1 over n. And so what we see is that since 1 over n is a defining sequence for the harmonic series, thus this is a divergent series, the limit comparison test is going to show that this series itself is going to be divergent. So here we'll say, note, the sum of the Bn is a divergent p-series. Observe that the limit as n goes to infinity of a sub n, which is the given sequence, over b sub n, 1 over n, is the same as the limit as n goes to infinity of n squared plus 2n over n squared minus 1, and we see that this is clearly a 1, which is both non-zero and finite. Thus, by the LCT, the sum of the AN diverges as well. So this is just a quick example we saw in class. The important takeaway is that this exists for rational functions, which are polynomials over polynomials. You can do the exact same thing if there's roots involved as well. So another example we could take a look at would be the exact same type of situation. Suppose it's going from 3 to infinity or something like that. But what if we had something like this? The top is the square root of n to the 7th plus 6n minus 1 all over, something like, let's go n to the, say, 4th plus 2n cubed plus 3. What we see is that the denominator's highest power term is easily still deducible, n to the 4th. The numerator, however, is a little murkier. However, the key takeaway is that the growth rate of this numerator is going to be the growth rate of the largest powered term in the root along with the root. So what that is this numerator is going to grow like the square root of n to the 7th. So what we're going to do here is we're going to consider the b sub n to be the square root of n to the 7th over n to the 4th, which in this case is n to the 7 halves over n to the 4th, which is going to be what? So the top is n to the 3 halves, so this is going to become the square root of n in the bottom. This, of course, is a divergent p-series. And so what happens here is, again, we're going to take a look at the limit as n goes to infinity. Notice that maybe I should be a little more careful as I write this. What we want to say is note that the sum of the b sub n is a divergent p-series. So when we come here and look at the limit, this is going to be the limit of the square root of n to the 7th plus 6n minus 1 over n to the 4th plus 2n cubed plus 3, all divided by 1 over the square root of n, which becomes the limit as n goes to infinity of, we're going to end up with, keep change flip, we're going to end up with the square root of n to the 8th plus 6n squared minus 1 over n to the 4th plus 2n cubed plus 3. And this similar process can be done. Maybe what you can think about is we can divide every single term by n to the 4th. Another way to visualize this is I could multiply the top and the bottom by 1 over n to the 4th. Doing that to the top amounts to multiplying the inside of the root by 1 over n to the 8th. So this will become, change our color back, the limit as n goes to infinity of the square root of 1 plus 6 over n to the 6th minus 1 over n to the 8th, all over, this will be 1 plus 2 over n plus 3 over n to the 4th. And we see here now that all of these terms are going to be going to 0. And so the only terms that survive, of course, are the first few terms, and so that's a 1, which is non-zero and finite. So this series a sub n is divergent by the limit comparison test. So I wanted to take a look at another example like this where roots are involved, because the process is exactly the same. Now what I'd like to take a look at is a sampling of the problems that were given toward the end of the handout. I might not do all of them, but I kind of want to discuss each of them so that you can follow along at home and fill in the details. So one of the first examples we saw is the series n minus 1 factorial over n plus 2 factorial. Now we don't know whether we need the direct or limit comparison test, but regardless, the first thing I want to do is simplify this. So if I simplify the summand, I'm going to get 1 times 2 times 3 times etc. all the way up to n minus 1 in the top, and the bottom will be 1 times 2 etc. all the way up to n plus 2, the penultimate item being n plus 1, then n minus 1. And the key observation here is that the numerator completely cancels with all but 3 factors in the denominator. So this is actually becoming the series from n equals 1 to infinity of 1 over n plus 1, n plus 2. Now, fun fact, this series, as written, this will actually telescope. We saw examples of this previously. We're going to have to do partial fraction decomposition, and then we can figure out what the sort of telescoping pattern is, and we can push through like that. However, if we're only tasked with determining the convergence or divergence, we don't need to really care that it's telescoping. The key observation here is the following. If I were to just delete the 1 and the 2, I get something that's bigger. So 1 over n times n plus 1 times n plus 2 is less than or equal to 1 over n cubed. And since the sum of 1 over n cubed is a convergent p-series, the direct comparison test says that the sum of n minus 1 factorial over n plus 2 factorial is convergent as well. So this is an example of making sure we read the directions and that we're careful about the difference between compute the sum and determine convergence, because one is going to be far easier to do. The next example we can run into is a great one. This one is the sum from n equals 1 to infinity of tangent of 1 over n. Now, admittedly, the solution to this one might not be blindingly obvious to begin with, but consider the small aside so that we can import some information. You might recall that the limit as x approaches 0 of sine of x over x is equal to a 1. Note that a 1, parenthetically, is both non-zero and finite. So if we can do a limit comparison test here where we have something that looks like sine x over x where x is going to 0, then we're probably in good shape. However, notice that this is equivalent to saying that if I take the limit as, say, x goes to infinity, as long as I replace whatever's inside the function and beneath it with something that behaves like it's going to 0, we're in good shape. Well, one such candidate for that is sine of 1 over x over 1 over x. Again, it's going to look like sine of 0 over 0, which we know is going to a 1. So this is also going to be equal to a 1. Well, tangent is just sine over cosine. And note that cosine of 0 is just a 1. So what I'm going to do in this example is I'm going to say, note that I need a 1 over n in the denominator to take the limit of. So that's going to be what I'm going to compare it to. The sum 1 over n is divergent. And the limit as n goes to infinity of tangent of 1 over n over 1 over n is the same as the limit as n goes to infinity of sine of 1 over n over 1 over n multiplied by 1 over cosine of 1 over n. This limit is going to go to a 1. That's what this entire sort of lemma is over here on the right. Whereas what's going to happen right here, well, that's going to go to cosine of 0. That goes to cosine of 0, which is just a 1. So this overall limit is actually just plain equal to a 1, which is both non-zero and finite. So by the limit comparison test, the sum of the tangent 1 over n diverges as well. And the interesting thing here is that this little recall item on the right, this is true regardless of what 1 over x is, as long as it's going to 0. So for example, a thing you can play with at home is, what if I looked at the sum, say, tangent of 1 over n squared? What you're going to want to do is you're going to want to do limit comparison test with, say, 1 over n squared. And you'll get a very similar set of circumstances. So this is a really nice example of recalling some Calc 1 limits to help find the convergence or divergence of a series that is somewhat more interesting. Another example we could work with is going to be this one. We have the sum of ln of n over the square root of n e to the n. For this one, notice that as soon as we see sort of ln of n's and square root of n's at play, we're reminded by the growth rates. So by growth rates, what do we know? We know that ln of n to any p is eventually dominated by n to the q for any p and q. Well, it's not for any, it's for any positive p and q. So we're going to choose, well, what if I choose my p to be 1, because that's the ln that's there, and I choose my q to be a 1/2? Then this will get larger by swapping the ln n for a square root of n. Those will cancel, and we'll be left with e to the n. And that might be a good thing. Let's find out. What we're going to do is witness that the ln of n is eventually dominated by the square root of n. So what that means is that ln of n over the square root of n e to the n is eventually less than or equal to square root of n over the square root of n e to the n. These cancel, and I'm left with just 1 over e to the n, which is the same as 1 over e to the n. But notice that 1 over e, well, that's less than 1. So this is a geometric series with common ratio 1 over e, which is less than 1. So the sum of 1 over e to the n is a convergent geometric series. Thus, by the direct comparison test, the sum ln of n over the square root of n e to the n is also convergent. So this is a good example again of using growth rates in order to determine the convergence or divergence of a given series. And this type of use of growth rate arguments is super common. There's other examples we can work through. We have this one that says that the sum of 3 to the n minus 1 plus 1 over 3 to the n, and going from 1 to infinity. What about this? Well, observe that if I were to just destroy this plus 1, I'd get something smaller. Well, so let's see what we get if we do that. If I take 3 to the n minus 1 plus 1 over 3 to the n, and I just kill off that plus 1, I get something smaller. Well, that simplifies into just a 3 in the bottom, 1/3 then. Note that the series of just 1/3 over and over and over again is divergent. So by the direct comparison test, the series we started with, 3 to the n minus 1 plus 1 over 3 to the n, is also divergent, by comparing it to literally sort of the silliest possible series. So sometimes the direct comparison test is really just that easy. The next example that we can run up against is something like this. We have this series of n over 3n plus 1 to the n. It seems immediate to me that this is a limit we sort of recognize. So an option is to sort of take n to infinity and see if you're going to get anywhere reasonable. That is, to see if you get something that's non-zero. But I think we can do better. Because notice if I were to just delete this positive 1 in the bottom, I'm going to get something bigger. So observe that n over 3n plus 1 to the n, well, that's less than or equal to just n over 3n to the n, which then I can cancel these n's, and I'm simply left with 1/3 to the n. Well, that's great news. This defines a geometric series. So the series 1/3 to the n is a convergent geometric series. So by the direct comparison test, the proposed series, n over 3n plus 1 to the n, is also convergent. And you start to see these common themes, the adding, the deleting of these extra things, this deleting of the 1 here. Again, here I deleted the 1. I think we did that earlier today as well. Here we deleted the plus 1 and deleted the plus 2. So it's a super common trick that hopefully you're starting to see more examples of. To get back at sort of the original topic of the video, we have the series 5n cubed minus 3n all over n squared n minus 2 n squared plus 5. The minute you see this, you want to aim for either a direct or limit comparison. I think the limit comparison test is the fastest here, because notice you can't just willy-nilly, cut off values. Here we have a plus 2, here we have a plus 5. Well, if I cut off the minus 2, I'm getting smaller. If I cut off the plus 5, I'm getting bigger, and it's not clear which direction you end up going at the end of the day if you kill both at the same time. So instead, what I'm going to do is I'm going to say consider b sub n, which is I'm just going to steal the highest powers. So the top is going to be 5n cubed. The bottom is going to be, if I were to FOIL it all out, I would just get n to the 5th. Well, that's 5 over n squared. And the series of 5 over n squared is a convergent p-series. Now, if I take a look at the limit as n goes to infinity of the original series, which is this whole rational sequence right here, and that's all divided by the new series, which is 5 over n squared, after I sort of simplify everything, what is this going to turn into? Well, I have to do keep, change, flip, and I'll end up with 5n to the 5th minus 3n cubed all over, well, if I were to FOIL this entire denominator with a 5, notice I'm going to end up with 5n to the 5th plus some other terms. And the point is, I don't care what those extra terms are, because the limit is completely dependent on the highest powered terms, which, as per usual here, is equal to 5 over 5, otherwise known as a 1, which is both non-zero and finite. So by the limit comparison test, the sum of the a sub n is also convergent. The last example that we're going to look at in this video, and the last example from the lecture notes, is going to be something that involves an interesting looking series that looks a lot like it could be a geometric series. This is the series of 2 to the n plus 3 to the n over 3 to the n plus 4 to the n. What I'm going to do here is I'm going to witness that if I were to swap this 2 with a 3, I'd only get bigger. And similarly, if I were to swap this 4 with a 3, I would also get bigger. So maybe instead of doing both of those at the same time, instead I'll simply change one. If I do both at the same time, they're going to cancel and I'm going to get something that's not useful. But let's just change the bottom. So here we're going to note that 2 to the n plus 3 to the n over 3 to the n plus 4 to the n is less than or equal to, keep the top the same, but on the bottom, replace this 4 with a 3, and if I divide by fewer objects, I get something larger. So here I'm going to get 2 times 3 to the n, which of course becomes 1/2 2 to the n over 3 to the n plus 3 to the n over 2 times 3 to the n, which becomes 1/2 times 2/3 to the n plus just 1/2. Note that if this is what I'm going to compare it to, note that the sum of 1/2 that will not work. Let's see. What is it that I want to try to say? I think the correct approach here is to observe the following. Okay, so let me explain why this won't work. Obviously, if I add 1/2 here, and I put a sum of just 1/2, 1/2, 1/2, 1/2, that's going to be infinite. And being less than or equal to something infinite is not helpful. The direct comparison test fails. So that tells me that the limit comparison test would have been the right approach. Notice that the fastest growing item in the top is the 3 to the n, and the fastest growing item in the bottom is the 4 to the n. So by using our same sort of analogy as earlier, I'm going to consider the series b sub n to be the series of the highest powered term, 3 to the n, in the numerator, over the highest powered term in the denominator, 4 to the n, which is the same as the series of 3/4 to the n. And here the common ratio is 3/4, which is less than 1. So this is a convergent geometric series. Now, let's take a look at the limit as n goes to infinity of the given series, 2 to the n plus 3 to the n over 3 to the n plus 4 to the n divided by 3 to the n over 4 to the n. Let's see if this turns into something reasonable. Here we're going to get the limit as n goes to infinity of 4 to the n times 2 to the n plus 3 to the n over 3 to the n times 3 to the n plus 4 to the n. And the hope is that these two objects will limit to something reasonable. Well, what we can do here is we can actually factor out a 3 to the n from the top and factor out of 4 to the n from the bottom, and this will become the limit as n goes to infinity of 4 to the n, 3 to the n times, this was going to be 2/3 to the n plus 1, and then the denominator is going to be the 3 to the n times 4 to the n times, now this is going to be 3/4 to the n plus 1. And now what we witness is that the 4 to the n's cancel, the 3 to the n's cancel, and since each of these objects in the n's are less than 1, the limits as n goes to infinity of these items is going to be 0, which means the overall limit is going to be equal to simply 1/1, which is 1, which is both non-zero and finite. So, by the limit comparison test, the series 2 to the n plus 3 to the n over 3 to the n plus 4 to the n is also convergent. So this last one I think is maybe a little bit the trickiest, and admittedly I thought we were going to go down the direct comparison route, but when we hit that dead end that said we were now larger than something divergent, that tells me I should try the limit comparison test, where when I tried the limit comparison test, again, we just isolated the fastest growing items in the top and the bottom, and that was my item to compare to. And when I take a look at the limit of the quotient, what I did was sort of just push through the limit, and then when I got to this point, there was a little bit of a sticky business involving factoring out the highest powered terms. But in some sense, factoring out the highest powered terms is very similar to the whole dividing by the highest powered term anyway. So it's actually all sort of in the same wheelhouse. But that's going to be it for this conversation. I wanted to look at some additional examples and finish off the ones we had from class, because I think these are all really useful and really helpful. If you have any additional questions on any of this, please don't hesitate to reach out. I'm happy to help, and I'm happy to have a conversation. Otherwise, stay safe, stay healthy, and I will catch you all next time.